All right, so this problem says at a particular instant, a 1 kg particle's position is r equal to that. Okay, so this is the position with respect to the origin. Its velocity is that, and the force on it is this. What is the angular momentum of the particle about the origin? Okay, so again, you can calculate angular momentum, torque, about any point. So we're going to calculate it about the origin, and this is the position. What is the torque on the particle about the origin? What is the time rate of change of the particle's angular momentum about this instant? Okay, so again, this is Newton's second law for rotational motion. And if you guys check your notes, what is the angular momentum? Angular momentum is denoted by L, and it's the vector r cross p. Okay, and the linear momentum is mass times velocity. Okay, so this is mass times r cross v. So this problem is about calculating a cross product. Okay, and so let's do that. And you guys, so I'll remind you about the cross product. Yeah. If you have done determinants, it's I, J, K, AX, AY, AZ, BX, BY, BZ. Okay, but of course, so it's I, here's the expanded form, AY, BZ minus AZ, BY plus J, AZ, BX minus AX, BZ plus K is AX, BY minus AY, BX. Okay, that's the cross product. Okay, that's the definition of cross product, and we're going to use this to find the angular momentum. The mass is 1 kg. The cross product is R is 2I minus 4J plus 6K. Okay. Cross velocity is minus I plus 4J plus K. Okay. And the units, so I'm going to combine the units. The units for angular momentum is kg, meter, meters per second. So meter square per second. Okay. And again, this combination of units doesn't have any name. Okay. Now, you can do the cross product using this formula, or also it's useful to remember the cross product of unit vectors. I cross j is k, j cross k is I, and so on. What is I cross I? 0, very good. Okay, and what is k cross j? What is k cross j? Very good, very good. J is negative I. Okay, so if you remember that, we can do that. Use here, it might be useful to do it that way. Okay, so let me do the cross product. All right, I'm going to go here. No. All right, so L is, okay, I cross I is 0, I cross j is k. So 2 times 4, 8k. Then I cross k is minus j, so that's minus 2j. J cross I is minus k. Okay, so the way you remember this is I cross j is k, and j cross I is minus k. Okay, j cross, so you go in circular fashion. J cross k is I, k cross I is k cross j is minus I. All right. All right. So where were we? J cross I is minus k, so that's minus 4k. J cross j is 0, j cross k is I, so that's minus 4i. Okay. Then you have the last term, k cross I is j, that's a minus 6j. Okay. K cross j is minus I, so that's minus 24i. Okay. And k cross k is 0. Okay, so we have the angular momentum, and now we can collect all the terms. So L is, we'll collect all the like terms, so there should be 2 of each. That's minus 28i. There's minus 8j. And plus 4k. And again, the units are kilogram meter square per second. So that is the angular momentum at that instance. At that instant. Okay, so again, here was the particle, and here's the velocity. Okay. And at that instant, the angular momentum was that. Okay. So a little while later, let's say if the particle is accelerating and its velocity changes, let's say a little while later there is the particle, and if its velocity is in that direction, then the angular momentum would be different. Okay, so we calculated the angular momentum at a given instant. Okay. And what did we get? So there's the value. Okay, I will calculate the torque in a second. Yes, somebody, you had a question there? Hello? Do you still have your question?
Yeah.
Okay.
Cross product.
Mm-hmm.
For the J term, the second term, is it always negative?
Okay.
Well, because I watched a video on YouTube, and he said the second term on the cross product, it is always negative. So.
Okay, so in your YouTube video, it was negative of AX BZ. So this term can be written as AX BZ minus AZ BX J. All right. So this is correct. Okay. Okay, so here's a determinant. Here's how you expand. Okay, if you have a question when I'm explaining it, you watch that. All right, let's go move on. I don't want to waste my time. Okay. So, have you guys done determinants? Okay. So, when you expand a determinant, you do it in terms of the minors. Okay. So you can expand it in terms of any row or any column. Yeah. So let's say we'll expand it in terms of this row. Okay. So I And the minor for that element is this guy. Okay. And then you get the power 1 to the power. This was the first row, first column. 1 plus 1, 2. So minus 1 to the power 2. You're adding the row number and the column number times the minor. AY, AZ, BY, BZ. Then we'll add the second term, minus 1 to the power first row, second column. 1 plus 2, that is minus 1 to the power 3. And the minor for that determinant is you eliminate this and that, so the minor is AX, BX, AZ, BZ. Okay, what is the third term going to be? Minus 1 to the power. That's K, first row, third column. 1 plus 3 is 4. And the minor is this guy. AX, AY, BX, BY. All right. And how do you, a minor is defined as AD minus BC. Okay, that's how you, that's the value of the minor. Okay. So this is 1 I, AY, BZ minus AZ, BY. The second term is, that's minus 1, and there's J minus J times AX, BZ minus AZ, BX. And this is plus 1, K, plus K, AX, BY minus AY, BX. Okay. And you can absorb the minus sign there, make that plus AZ, BX. And that's what this term is. Okay. All right, so the cross product can be written in terms of determinant, which I expanded here. And of course, you don't want to be doing that all the time, so you just remember that. Okay. So there's the cross product. Now we'll find the torque. Angular momentum was R cross P. Torque is R cross force. Okay? So and so R is our vector. R is 2i minus 4j plus 6k. 2i cross, and the force is 10i plus 15j. 10i plus 15j. And the torque is Newton meters. Okay, again, in the past, Newton meter, that combination was called a joule, but that was when we were talking about energy. So when we are talking about torques, we leave it as Newton meter. We don't write it as joules. Yeah? All right. So this is I cross I is 0. I cross J is K. So that's 30K. J cross I is minus K. Okay, J cross I is minus K, and you have minus 40. So plus 40K. Here's a thing to notice. What is this vector? What this vector is in the xy plane. The cross product of any two vectors is perpendicular to that plane. Okay? So if this is in the xy plane, you know that the cross product has to be in the z direction. Okay? So you want to be able to notice stuff like this. So we already got two terms in z, okay? And you won't have any non-z terms, okay? So we did that. I cross I was 0, I cross j was k, j cross j was 0. Okay, so we have to do this. Oh, this we already did. K cross I what happened? Okay, so let's see. K cross I is j, so plus 60j. Oh, what happened? Oh, okay, never mind. So this was in the xy plane. Okay, so my bad. This was in the xy plane. Here was another vector. That could be in, doesn't necessarily have to be in the j direction, okay? So it's perpendicular to that plane. Okay. So my bad. Okay, k cross I was j, and then k cross j is negative I. So that's 90 minus 90I. Okay, Newton meter. So minus 90I plus 60J plus 70K. So that is the torque, Newton meter. All right, so there's the cross product. And then part C asks, what is the time rate of change of the particle's angular momentum at this instant? I'm sorry? And Newton's second law states the torque at any given instant is time rate of change of angular momentum. So the time rate of change of angular momentum at that instant is that. Okay. So this angular momentum at this instant is changing at this rate. Okay. So this is the angular momentum at time t equal to 0. In 1 second, the angular momentum will have changed by that much. Okay. So if you are to write the angular momentum 1 second later, it's angular momentum at time 0 plus this change. Okay. So it would be 1 second later, this would be the angular momentum, which would be this vector plus that vector. Okay. All right, so that's what all that means. All right, the next problem says a boulder of mass 20 kg and radius 20 centimeters rolls down a hill 15 meter high from rest. 15 meter high is roughly 3 times the height of this room. What is the angular momentum when it's halfway down the hill? Okay, so here we are going to assume it's rolling down without slipping. This is 15 meters. Okay, I'll calculate at the bottom, and if you want it halfway down, just replace that by a hill 7.5 meters. Okay, so it'll be the same. Okay. What is it that we want to find? What is its angular momentum? Okay. So what we'll calculate is V center of mass, omega. So What we'll calculate is the velocity of the boulder at the bottom, which will be related to the angular velocity, and angular momentum is I times omega. I, the moment of inertia, is 2/5 mr squared. So for a sphere a solid sphere of uniform density, moment of inertia is 2/5 mr squared. So here's a table that you can look it up. So here's a solid sphere, and the moment of inertia about a diameter is 2/5 mr squared. Okay. So you'll be referring to this table. All right, so we want to calculate this. We want to calculate angular momentum at the bottom. We know this formula. We know the moment of inertia. Now we got to calculate final angular velocity there. Yeah. And you guys can, okay, so, all right, let's go back there and, okay, I guess I need a, okay, so here's the formula for the velocity of an object rolling down the hill at the bottom of the hill. Okay, 2gh. So there's the formula. So the velocity, the center of mass velocity at the bottom of the hill is 2gh 1 plus I center of mass divided by mr squared to the power half. Okay. There. So this is the formula I copied. Okay. All right. So we can calculate this, and omega is related to is r times v is r times omega. V center of mass is r times omega, and so omega is v center of mass divided by the radius of the boulder. Okay. So we're going to calculate the center of mass velocity there, then get the angular velocity, and then get the angular momentum. Okay. So let's do that. The center of mass velocity is 2 times g is 9.8 meters per second squared. Height is 15 meters. 1 plus, okay, the moment of inertia is 2/5 mr squared. That divided by mr squared will give you 2/5. 2/5 is 0.4. So that becomes, okay, all right, I'll write it as 0.4 to the power half. Okay, so the center of mass velocity, and I'm doing part B. So center of mass velocity works out to 14.5 meters per second, and omega is v center of mass divided by r, so 14.5 divided by radius is 0.2 meters. And so that's 5 and 15 times 5 is 75, so 72.5 omega. It's radians per second. So just, that's the angular velocity. And so the angular momentum will be I times omega, which is 2/5 mr squared times omega. Mass of the rock is, boulder is 20 kgs. R is 0.2 meters. And we just calculated this to be 72.5. Okay, the units would be, again, kg meter square per second. Okay, so that's the angular momentum. Okay. All right, angular momentum is I times omega, and as the boulder rolls down without slipping, its angular velocity is increasing, and the angular momentum is increasing. Okay. Its linear momentum is also increasing. The velocity is increasing. Okay. So linear momentum at the bottom would be mass times velocity, which would be 20 kgs times, what was the velocity, 14.5 meters per second. So this is 29, 290 kg meters per second. So there is the linear momentum at the bottom of the hill. Okay, so here is an interesting problem for those who are interested in astrophysics. A pulsar is a neutron star. Okay. So again, we talked about this. Here is the symbol for the mass of our sun. Okay, and the mass of our sun is 2 times 10 to the 30 kgs. To put this in perspective, mass of Earth is about 6 times 10 to the 24 kgs. Okay, so the sun is, that's 1 million times greater, 1/3 of a million times, so about 330,000 times more massive than the Earth. Okay. A star becomes a neutron star if the mass of the neutron star is between 1.4 solar masses, less than 1 solar. Oh. So this is a neutron star. A star can become a neutron star if its mass is between 1 and 3 solar masses. So this is just above that limit. Okay, so this is here's a star that's become a neutron star. It's called a pulsar if so a neutron star is a very dense object. Okay, here's the a neutron star is spinning very fast. It could be spinning 1,000 times a second. You see the dimensions of this. its radius is 10 kilometers. The radius of the Earth, the radius of the sun, you can Google it. Okay, let me Google it. Okay, so 700,000 kilometers. So the radius of the sun is 700,000 kilometers. And so we'll say 1,000,000 kilometers, and it becomes 7 kilometers, roughly 7 kilometers. For if the sun were to become a neutron star, its radius would have to decrease by a factor of 100,000. Okay. The sun is spinning once a month, and you guys have seen videos. If an ice skater is spinning and he or she pulls her arms in, she's spinning faster. Just like that, when this star collapses into a neutron star, a tiny neutron star, remember its radius is decreased by a factor of 100,000. It will spin very fast. Okay. So very massive object. Now it's become the size from here to Ormond Beach, and it's spinning fast. Okay. Do you guys understand? Do you guys understand all of that? All right, so now the point of all this story is, now with the physics that you're learning, you can understand all of this. Okay, so here's a neutron star. How big is this? The radius is 10 kilometers from here to roughly Ormond Beach. And oftentimes, neutron stars will be formed where their magnetic axis is not lined up with the rotational axis. If this guy is lined up with the rotational axis, then it's not called a pulsar anymore. It's still a neutron star. Okay, now we'll figure out why it's called a pulsar. Okay, so if the magnetic axis is not lined up like this, okay, all right, along the magnetic axis, what happens is it emits radiation. What happens is particles spiral around the magnetic field lines, and you get electromagnetic radiation coming out in this direction. So it's like a lighthouse. There's the beam. All right, so here's this neutron star rotating about that axis, and this beam is sweeping the sky. So there's the beam sweeping the sky like that. And if you happen to be here, if Earth happens to be here, then that beam will hit you 1,000 times a second. Okay? So if that beam is hitting you, you're getting a pulse, a strobe light 1,000 times a second. And that's how the pulsar was discovered. And actually, the person who discovered the pulsar, Miss Jocelyn Bell, she's come to Embry-Riddle 2-3 times to give a talk. So she should have won a Nobel Prize, but of course she didn't. Anyway, all right, so that's a neutron star. Yeah. So this is what we're going to talk about. And again, all right, so a pulsar is a rapidly rotating neutron star. The Crab Nebula pulsar is in the constellation Taurus, has a period of 33.5 milliseconds. Okay, so what that means is that it's spinning once in 33.5 milliseconds. Okay, all right. So it's spinning once in 33.5 milliseconds. So and the beam that is hitting us hits us every 33.5 milliseconds. Okay, that's what that means. You guys have seen those St. Augustine lighthouse. You can time the St. Augustine lighthouse again, and so that's hitting us every 33.5 milliseconds. The radius of the neutron star is 10 kilometers. And it has a mass of that. So the pulsar rotational period will increase over time due to the release of electromagnetic radiation, which doesn't change its radius but reduces its rotational kinetic energy. Okay, you're radiating energy, so you're losing energy, and that, as a consequence, you slow down. Okay. And so we have accurately measured this, so the period will increase. Okay. Which doesn't. What is the angular momentum of the pulsar? We'll calculate the angular momentum. You already know how to calculate the angular momentum. You're experts at it. I omega. What is I? This is 2/5 mr square. And omega is, what is omega? It's rotating 2 pi radians every period. Okay. So that's how you calculate angular momentum. Okay. So that'll be A. B, suppose the angular velocity decreases at the rate of that. What is the torque on the pulsar? So they give you the angular acceleration is 10 to the minus 14 radians per second square. And so what is the torque on it? It's I times alpha. Yep. 2/5 mr square times alpha. Okay, I'm not going. All right, I'll calculate one thing for you guys. 2/5, the mass of the pulsar is given, the radius is given, the period is given, so you can calculate that. The mass is given, radius is given, and the angular acceleration is given. Okay, you can calculate that. So I'll calculate this here. Okay. So let's calculate the angular momentum. Mass is 2.8 times 10 to the 30 kgs. R is 10 kilometers, and you want it in meters, 10 to the 4 meters, R square. So there's the moment of inertia. And then angular velocity was, so 2 pi radians divided by 33.5 into 10 to the minus 3 seconds. So it's a millisecond pulsar. Okay. So when you hear millisecond pulsars, that means it's roughly rotating 1,000 times a second. Yep. All right. Now the reason I'm calculating this is because I want you to see, take care of the powers of 10. So this is 10 to the 30, that's 10 to the 8, 10 to the 38, plus 3, 10 to the 41. Okay. Then 2/5 into 2.8 into 2 pi divided by 33.5. And what are the units? kg, meter square per second. Okay. All right, so that's 0.4 into 2.8. So there's the angular momentum of the pulsar. Okay. Okay, so let's compare that to the angular momentum of that rock that was rolling down the hill. So a 20 kg rock is about a 50-pound rock. At the bottom of the hill, its angular momentum was 2 times 10 to the 23. Okay. So the angular momentum of the pulsar is 10 to the power of 39 times greater. A trillion, 1,000 trillion times greater. Yeah. All right, so I'll do this one problem because this is also interesting. I'm sure there are video recordings of the other problems. This problem is also interesting, but I want to get to chapter 12. Okay, so here is here's a space station that consists of a giant rotating hollow cylinder of mass 10 to the 6 kgs. Okay, so if you wanted to do interstellar journeys, okay, so here's how you would do that. Okay, so your space station, will be something like this. Okay, there's the axis of rotation. You would be rotating like that, and this would be, people would be living on the inside surface. Okay, if the space station is rotating, the force acting on them would be like this. Okay, so when you're standing on the ground, the force on you is downward. Okay, so, and that's the direction in which plants grow. So you would be planting stuff here. Plants would grow this way. There are the roots of the plants. Okay. And well, how big is this cylinder? So has a radius of 100 meters. This is 100 meters. So this would be the space station. So imagine a cylinder. Excuse me, hello there. Can you hold up your can, soda can? Yeah. So imagine a cylinder like that, except that the radius of that thing is from here to Mainland High School. And you're living on the inner surface. Okay. And then this travels, whatever, you know. If you're going to go anywhere, you'd better be traveling fairly fast. And if you want to feel weightless, all you have to do is go to the axis and you'd be weightless. All right, so that's your future space travel. Okay. A space station consists of a giant hollow cylinder of mass 10 to the 6 kgs. That's 1,000,000 kgs. Okay. Now, to launch 1 kg, you need roughly 100 kg of fuel. So all this would never be possible without reusable rockets. So, you know, so that's what SpaceX has done for you guys. All right. It is rotating in space. So this guy is rotating in space at 3 revolutions per minute. So angular velocity is 3 revolutions per minute. We'll convert this to radians per second. Okay. So pi by 10 radians per second. Okay. in order to produce artificial gravity. Okay, so you feel gravitational force in that direction. Yeah. If 100 people on the average of mass 65 kg spacewalk to an awaiting spaceship, what is the new rotation rate of when all the people are off the station? Okay, so the problem is angular momentum collision problem. So what we are doing is 100 people got onto the space station, onto a spaceship, and went off. So the mass of the space station decreased. By how much did it decrease? 65 kg times 100 people. 6,500 kg. The mass of the space station was 1,000,000 kg. Okay, so it decreased by a very small amount, about 1%. Okay. So let me show you another picture. So let's say this is a merry-go-round, and the merry-go-round is rotating, and let's say you jump off the merry-go-round. What will happen to the spin rate of the merry-go-round? I'm sorry? It'll spin faster, and so that's what will happen for the space station. Okay. All right, so this is a conservation of angular momentum. This is like a collision problem. So initial angular momentum is final angular momentum. I initial omega initial equal to I final omega final. Omega final is what we're calculating. I initial over I final times omega initial. Okay. What is I initial? I initial is the moment of inertia of this, the space station, plus all those people on the rim. Okay. Now this is a shell. The moment of inertia is mr square. So the initial momentum is mass of the space station times r square. It's like a ring. So all the masses at distance r, plus mass of the people, and they're also at r. Yeah. So this is 10 to the 6 times 100 square plus 65 into 100 people times 100 square. Okay. So this is that's 10 to the 4, 10 to the 10, plus this is 4, 6, 65 into 10 to the 6 kg meter square. Okay, so this is the contribution of the space station to the moment of inertia. This is the contribution of the people to this moment of inertia. Okay, so that is equal to 1.0065 into 10 to the 6 into the 10 to the 10 kg meter square. What is I final? It's just the space station, 1 times 10 to the 6. Okay?
Is it supposed to be 10 to 10?
Yeah, 10 to the 10. What I'm saying and what I'm thinking are two different things. So omega final is I initial divided by I final times omega initial. Okay, so the space station speeds up by a very small factor. Okay, so it speeds up by 0.65%. Okay. So when it's sped up, so when people left, what happened to the artificial gravity? It got stronger. Okay. So now here's a side view of it. So the centripetal acceleration, which is the artificial gravity, is v squared by r, which is r omega by r. So your centripetal, your centripetal acceleration, which is your artificial gravity, is r omega squared. So when you sped up, your gravity increased. Yep. That's what happened. All right, but it increased by only 0.65%. No, I mean less than that. 0.65 times it was omega squared, so increased by a lot less than that. Yep. 0.3%. 0.3%. All right, guys, we will stop.